The goal in establishing a library of functions is to start to move away from the idea that to graph something we have to calculate and plot a whole bunch of points and only then see what shape it has, and instead start to look at functions and predict their shape and see what we can tell just by looking at the details of the formula. So we're starting with a few examples of powers and roots. The graph of y equals x squared is usually pretty familiar as what we would call a parabola. A parabola is a smooth graph. It doesn't have a sharp point at the bottom. It's a smooth graph, kind of more like a U shape that turns around, right? Understanding the parabola then helps us to understand the shape of the cube function. If we just look at the first quadrant, then we can see that there aren't a lot of differences between the graph of y equals x squared and y equals x cubed. Both of them are arced upwards. Both of them are increasing off to infinity. They have the same approximate shape here. The real difference comes in when we start to consider negative values of x. If x is negative, like for example -3, and I square it, I get a positive value. If x is a negative number, like say -3, and I cube it, I get a negative value. So the graph of y equals x cubed looks like if we were to take the other side of the parabola y equals x squared and flip it over, right? If we were to take this part of the parabola and grab it right here at the origin and make it go down instead of up, we would have a shape that looks like what we see in the cube function. It has a funny little moment here where it becomes horizontal, but then it just keeps going in the same direction. So the cube function is always increasing, whereas the parabola starts out decreasing and then changes to increasing. Once we've understood both the square and the cube function, we're prepared to understand the roots that go with them as well. For a parabola, if I were to consider, instead of y equals x squared, if I were to consider x equals y squared, that graph would be a parabola on its side, which would look like what I get if I fill in a bottom half below this square root graph. But because if I solve this for x, I get if I solve this for y, I get y equals plus or minus the square root of x. That tells me that the top half of the parabola is y equals the square root of x, and that the bottom half of the parabola is y equals minus the square root of x. So when I solve it for y, it breaks into two pieces. The graph of a square root function is just the top half of a parabola that's on its side. And cube root looks just like the cube function, but it is oriented about the x-axis instead of being oriented about the y-axis. It changes the orientation so that the graph looks like it's more closely following the x-axis here instead of the y-axis. Here we have a few more function types with some degree of familiarity. The identity function is the most basic linear function. This is y equals x, so this has a slope of 1, and it passes through the origin because the y-intercept is 0. So we can see it passes through the origin, and a slope of 1 means it's coming up at this 45-degree angle, cutting the first quadrant and the third quadrant directly in half. A constant function we also already know to be a horizontal line. And we've seen some absolute value functions and seen that they generally have a V shape. The most basic absolute value is just that y equals the absolute value of x. So this is just like taking the line y equals x that we saw up here and turning it into a V where it touches at the origin. Y equals 1 over x might be a little bit new. This graph has what we call asymptotes. It has a horizontal asymptote at the and it has a vertical asymptote at the y-axis. These asymptotes are just lines that the graph gets closer to without ever actually reaching. So as you go further and further out, in the case of a horizontal asymptote, as x gets larger or further from zero, it could be becoming a very large negative number as we see over here. The graph is getting closer and closer to that x-axis. In the case of a vertical asymptote, here as x gets closer to zero, we can see that our y values are growing without bound. This is a topic for rational functions. For now, we're just going to look at this one graph and accept that that's what the base case looks like, and that it would be possible to draw transformations of this graph according to what we're about to learn.